Assalamualaikum warahmatullahi wabarakatuh. So let us continue with subchapter of percent impedance of the transformer. So I have divided into 4 parts actually for this particular topic, and this is gonna be the last part where we have example on how we can calculate the percent impedance according to the nameplate or information given in this transformer nameplate. All right. So the following work example shows how the percent impedance of a transformer is calculated from its short circuit test data. So this is one of the method. Short circuit test we could carry out. So in order to calculate the percentage or percent impedance. Okay. So when the LT, so this is the stands for low tension secondary of a two winding transformer was short circuit, then full load primary current was obtained when the primary voltage was increased to 461.3 volt. So this is the method when we uh, short circuit, okay, the secondary part of the low tension transformer. So full load primary current obtained, and then the primary voltage was increased to this level of voltage. Okay. Then calculate the percent impedance of the transformer. So transformer has the following specifications. So this is what we can see from nameplate, okay, from here. And this is the high tension voltage. So the rating is measured at 11 kV. So low tension voltage is given by 415 volt SLSD, as well as the S rating, the apparent power rating kVA, which is 200 kVA. So solution full load primary current. So this is the equation. We do have the S equal to square root 3, right? The L, so just IL. So this is at a full load. FL stands for full load. So right this way. So the full load primary current. So we rearrange the equation into this, okay, and then just substitute the value of S, which is 200 kVA. This is actually we can see from previous slide. So this is 200 kVA, and with L in this example. So this is from high tension. Okay, VL or high tension load line or load voltage. Okay, so from there we are able to calculate the full load primary current. Okay. So this is okay. Sorry, this is 11 kV. So 11 kV from the nameplate of this high tension. Okay. Sorry, this is from here. All right, then after we calculate the full load primary currents, now we can actually transform the equivalent circuit of the transformer. So based on the short circuit test, so this is the IP, so this is our transformer impedance, okay. So this is the coil, so this is the secondary part where we short circuit. All right, we have a short circuit test. So here part, okay, this line is being short circuit. ISC stands for short circuit. Okay, so we do have a maximum current flow at the secondary part. Okay, after we short circuit the circuit or short the circuit. Then VP, this is the measured value of primary voltage for 61.3. Okay, after the full load primary current flowing inside the circuit or inside the network. Okay. So from here we can actually find the VPPU, IPPU. Okay, so we convert everything into per unit. and this is I short circuit P, PU. Okay, everything in per unit. Okay, so some of the relationships we can later derive, starting from per unit impedance, where ZT equal to VP IP. This is actually basically the Ohm's law, right? So the Ohm's law, VP PU over IP PU. Again, so we expand it, or we derive this into VP actual over VP base and IP PU. So we expand this equation into IP actual over IP base. Okay, rearrange. So we have IP actual, VP actual over VP base multiplied by IP base over IP actual. So this is the derived formula we can obtain, alright, to represent ZT PU. Okay, because in the beginning of this analysis or in the question, so we were asked to calculate the ZT PU. Okay, so then from there, at now, what happened at the primary side, VP, the base of primary voltage, is equal to the rating voltage of primary part of the transformer, or the VP rated. Okay, so we just pick VP base as the from the VP rating, okay, or the rated VP. So when the secondary is short circuit, so what happened after the secondary part is being short circuit, the primary voltage is increased until the secondary current flowing as is at its rated value. Then, so at this particular situation, so the IP actual equal to IP full load, right? So the actual full load, and we pick this as IP base as well, all right? So the actual is equal to the IP load since the secondary part is short circuit, okay? Then this has been picked as IP base as well, all right? And then from this relationship, IP actual equal to IP load or equal to IP base. So this two are into this, all right? Base is here and actual is here. Okay, so we can say this is all this equal to 1. Okay, because they are equal, the top and the bottom one. So they're equal, and then VP actual, okay, equal to the VP measured. So after after we short circuit the secondary part, so we go to the terminal of the primary side of the transformer. So we may measure the voltage, all right? So the rated voltage or the operating voltage. By that time, we know that the one we measure is actually the actual voltage, all right? So, and then this VP actual equal to VP base. So we just substitute into this, okay, here. This means this VP actual is, in this particular situation, equal to VP measured. So we have cancelled out the I quantities, okay, IP base over IP actual, because they are 1, okay, they are equal to 1. So now we have a simplified equation where now we have VP measured over VP base. So here we go, all right. So after we simplified the derivation, so the ZTPU, the transformer impedance in per unit, is equal to VP actual over VP base, and we know that VP actual, again, this is equal to VP measured over VP rated. Okay, in this example, so this VP base, is equal to VP rated over here. So therefore, VT percent, okay, or percent impedance of VT, this is equal to VP measured over VP rated multiplied by 100%. 5%. Okay. Then from our example, so VP measured is given here, and this is the VP rated 11 kV. So just take from measured voltage 461.3 over the rating or rated voltage. Okay, the voltage rating, which is 11 kV. And now the ZT, okay, percent is equal to 4.21%. Okay. So if you go back to the nameplate, so you will see here the impedance is written as 4. Okay, 4%. This is the unit of, this is the symbol of percentage. So this is the number 4. Okay, it's about 4%. So additional information. So in today's transformer, percent impedance varies between 2 to 6% for distribution units and 6 to 25% for power transformer. Okay, this is for the general knowledge. So exercise in a short circuit test on the step-down transformer, it was found that the primary voltage of 600 volt was required, okay, to circulate full load current in the secondary. So this is what we can measure. We measured from the primary terminal, and then the HB primary rated voltage. So this is the rated voltage. So again, this is the measured. So this is the rated voltage. And then from here, you can easily calculate the percent impedance of the transformer. So answer is 5%. So you may do it yourself. So some of the tips during the job seeking interview, for example. So the question, if you were to work or to be employed by a transformer company, so for instance, so they may ask you this basic question. All right. So how is the percentage impedance of a transformer measured? So you may go to this slide and this slide, back to this slide in order to explain or to answer the question. All right. So make sure you short circuit the secondary terminal or the secondary output of the transformer before you may get the full load current flowing in the primary part of the transformer, etc., etc. Okay. Then what about how about the other equipment? So this is very straightforward. So in general, the percent impedance of an equipment is calculated as follows. So we have Z actual over Z base. Okay, so where Z actual is the experimentally measured in impedance, and so this is we directly measured. Okay, and then Z base, how to find Z base? Okay, the actual we measure again, so we just measure experimentally, and then Z base we need to calculate from V base square over S base. So the base voltage is rated voltage of the equipment, or the voltage rating in a nameplate, for example, you can simply find from there. And the base power is the rated apparent power. Of course, this S base is the rated apparent power, basically represent in volt ampere, okay, of the equipment. So another example, a transformer rated at 200 kVA. So again, so this is the apparent power. So as rating 200 kVA, 250 kVA. Then this is the ratio. Okay, it's a step down transformer. Okay, the turn ratio also can be calculated from here. And so this is the frequency, operating frequency 50 Hz, has an impedance of 5.1%. Okay, the ZT, the transformer impedance. So calculate the base impedance on primary and secondary side. Okay, both base impedance, the Z base of both sides. So you have to calculate. And then the total internal impedance ZT of the transformer referred. So this is the main trick is referred to the primary side. So once you refer to primary side, so you have to be careful with the Z base you are choosing. Okay, so make sure primary side basically we refer as base 1. Okay. So base impedance on the primary side is Z base 1 equal to E1 squared over S base. So this is 11 kV. So this is basically coming from the basic equation V base. Okay. V base 1. Okay. So it may also represent in this symbol. This is also equal to E1. Okay. Or E base 1. Okay. Simply like this. Okay. 11 kV. So you may pick from here. Okay. 11 kV up here. Okay. Into this equation. Square it. And we have the S 250 kVA into here. Okay. And giving S base 1 equal to 484 ohm. So base, this is for Z base 1. So how about Z base 2? So similar process, we have the E2 or E base E2, square it, we pick from 415, okay, into here, and the S base, okay, 0.689 ohm, the Z base 2. So the actual value of ZT on the primary side is, again, so this is, if you refer to primary side, so make sure you pick Z base 1, the one you have calculated here, 848 ohm, so multiply by the ZT, okay, ZT of the transformer, which is 5.1%. Okay, the actual, this is basically in PU, 5.1, you have to divide it by 100 in order to get the PU. So remember, this is what we have learned in earlier notes. So the PU, so in this particular example, so we have 5.1, so just directly divide by 100. So this is the method. Remember, divide by 100, so you can get the PU ZT is 0.0551. Okay, so here, and multiply by the Z base 1 484 from here again. Okay, and then we can get the actual value of ZT on the primary side equal to 24.684 ohms. So another good work example. So a generator is rated 1000 volt ampere, the S, and 200 volt. So I believe this is gonna be later on as our V base. Okay. This one too. This is, I believe, later on we will pick as base. Right. So and has impedance of 25%. Okay. And then stamped on the nameplate together with other rating. So if the generator above is short circuit and its terminal, find the short circuit current and the short circuit power delivered by the generator in PU. So you need to find, okay, short circuit current, the short circuit power delivered by the generator in PU, and then in PU, so in percentage, and also in the actual value. Okay. Solution. So this is the diagram, the circuit diagram of above question. So we have the generator impedance ZG. Okay. So this is generator. Okay, it's not transformer. That's why we have a different notation over there. Generator. Okay, only one side. Okay. So generator impedance ZG equal to J 25%. So EG, so this is the generated voltage of the generator equal to 200 volt. Okay, and then we short circuit the terminal. We do have the short circuit current flowing inside this circuit, for example. Okay. Then choose the rating of the generator as the base value. So we have base 1000 volt ampere, V base 200 volt, and then from here we have done again S and V. Now we move on to I base. S base equal to V base, 5 ampere is the answer, and then Z base, okay, V squared over S. Now we have 40 ohm for the answer. Okay. So now calculate the per unit impedance of the generator. Okay, divided by 100. So we have G 0.25 pu. Okay, the actual impedance in ohms. So we have G actual. So the pu is here. Okay, here, and multiplied by Z base, which is 40 ohm. Okay. 40 ohm. So now we get the actual V G, which is J10 ohms. So calculate the short circuit current. So EGPU, ICPU over equal to EGPU over ZGPU. So this is divided of 1, I believe, EGPU. So we just directly pick from here. Alright. So this is the actual 200, and this is also the base. So we can have 200 the actual over 200 the base. Okay. So the base value of the G. Okay. Then we can get this is equal to 1. Okay. PU. So into here, and then this VGPU. So this is from earlier calculation into here, and then now we have 1 over J 0.25 is equal to negative J 4.0. So this is basic mathematics. So how to solve 1 over J 0.25. So this is equal to 4 over J, isn't it? Okay. And then to eliminate J, okay, the below J, so you have to multiply with J. Okay, sorry. So we start with 4, multiply by J, and here J multiply by J. So give you J 44, sorry, over J square. Remember where J is coming from? We do have J square equal to negative 1. Okay. So J square equal to negative 1. So this is why the J symbol is coming from the imaginary part, because we cannot actually square root negative 1. So there is no any possibility to get the answer of this operation, negative 1, square root negative 1. So this is where the symbol of J comes from. So by having that, you know that J square is equal to negative 1. Then substitute this negative 1 into here. So we can get this is equal to J4 over negative 1. So this is basically negative J4. Okay. Here is the answer, negative J4 PU, of course. So what about the percentage? So just multiply by 100. So 4.0 multiplied by 100, giving negative J for 100%. Okay, the short circuit, or the short circuit current in percentage. So calculate short circuit power delivered by the generator. So this is the basic calculation, or the basic equation as CPU E or V. This one can be V, so multiplied by I, conjugate short circuit T PU. So conjugate from a negative J to make sure this is become positive due to the conjugate equation. So now we have positive J 4.0 PU. Again, to convert into percentage, multiply by 100%. Okay, here 400%. So now calculate the actual values from the per unit values. So I short circuit, this is equal to I short circuit PU multiplied by I base. Right, so J negative J 4.0 multiplied by 5 I ampere. This is the I base we calculate in the beginning of analysis. PV negative J 20 ampere again. From here for the S short circuit actual, so PU multiplied by S is okay. So PU again pick from here into here multiplied by 1000 is the kVA base. Okay, giving J 4000 volt ampere. So this is the exercise. You can try yourself, solve the load voltage and load power. So the load voltage VL, SL, VL. So you need to calculate the load voltage VL, the load power PL in the circuit shown below using the PU analysis with an S base of 100 MVA megavolt ampere and voltage base of 8 kV, okay, 20 kV and 16 kV for each zone. All right, so zone number 1, okay, zone number 2, and zone number 3. Okay, the base value. Okay, don't forget the ratio and 1 to 10 as well as 5 to 1. Okay, so this is the provided answer for you to have a cross check. So advantage of per unit system, there are mainly two advantages of using the PU system. So the parameter of the rotating electrical machine, okay, the rotating electrical machine, the parameter, the coil, the impedance, the resistance and all that, and the transformer lies roughly in the same range of numerical values irrespective of their rating, regardless their rating, okay, the V, the I, the S, and etc. So they are being disregard because we do only concern the numerical values, okay, without the units, ampere, ohms, voltage, watt, okay, VA, etc. etc. Okay, if we do express in P unit system, okay. So then the second advantage, calculation are simplified because quantities expressed as per U, okay, the per unit. So in the between, okay, in the middle of the analysis, every quantity is being expressed or transformed into per unit. So where they do not actually change when they are referred from one side of the transformer to the other. Okay, so you may later on refer to primary or secondary. Make sure you pick the correct base value in order to get the actual quantities. Okay, whether voltage, current, ohm, etc. etc. Okay. So the end of the slide. Thank you very much. So we see you later in similar topic 8, but this is more to the complex power analysis. Okay. So thank you again. All the best.